Good morning, everybody. Is this working? Yeah, you tested. We are delighted today to welcome Leonardo Chiappisi. Never really know how to pronounce his word. He has an interesting profile because he comes from Sicily, but he also has a German nationality. So I don't know how this must be funny in their family, Sicily and Germany together. It makes an interesting mix. So Leonardo studied chemistry still in Palermo in Sicily, and then he decided that he needed to follow his German roots and moved to Berlin for his master's, for a chemistry master's, and did his PhD in the group of Michael Grazielski. I don't know if this is a name which is known to the audience, on polyelectrolyte surfactant mixtures. So already very much soft matter and physical chemistry, not so much chemistry anymore. After his PhD, he got a fabulous position between Berlin and the ILL. I never know how to say ILL in full words. Institut Langevin, in Grenoble, to use neutrons to look at soft matter systems. And he was working for 5 years in between Berlin and Grenoble, but I think mostly in Grenoble. And then they realized at the ILL that he was a good guy, so they tried to keep him. He stayed there as a scientific coordinator and is now officially head of the soft matter lab. So he's not a beamline scientist, but he has a soft matter lab with a lot of non-neutron based equipment, and he accompanies people with additional experiments, develops new soft matter science at the ILL, and he also does a lot of nice work on foams, and he will talk about his work on foams today. And an interesting information is that actually a lot of this work, the initial work, was done with an excellent PhD student who was trained in Strasbourg. So he was a former Strasbourg physics student. We tried to keep him, but he did his great work in Grenoble. So the floor is all yours.
Yeah, thank you very much. Well, I use this one. Being Italian, I need 2 hands to talk. Yeah, thank you very much, Wipke, for the invitation. And already in the one day I've been here, learned a lot of things. So thanks also to students I could talk with, and thanks to you to be here. And it's always difficult for me, let's say, when starting for the seminars to decide how to start a seminar. And for this audience, I think it's particularly challenging. I said once, I don't want to start talking what the applications of forms are, nor to the fact that forms are multiscale structures. It's all things you know well better than I. So then I decided, well, I might start with an anecdote on how this thing started. So it was all about 2020. Was still working on polymers and surfactant mixtures, happy days at the time. And Olivier Dier came to me and said, hey, Leo, we want to study forms and we want to probe the structure of these forms. Can you help me with that? But yeah, sure. It looks pretty straightforward. My main business was in this domain, looking at surfactants, how they assemble and how they assemble into hierarchical materials. So, okay, then you have some foam films. They don't look so ugly either. And then, well, you take a picture and you know what the macroscale structure is. So this is a main lesson. We badly underestimate the complexity of things when we don't know them. And maybe when we start learning about them, then we still underestimate how complex they are. Still, so they come when we, in this story, then entered Julien, who has studied here, came to the ILL and has done for most of the things which I'm presenting, all the initial part. I'm deeply grateful to Julien for his commitment and his work which he has done. So the idea is, okay, so this you can probe in principle by small angle scattering, and this macro scattering you study in real space methods. And until here, I don't see why it's so difficult. But then I realized then, if we want to understand the properties of these foams, maybe here in the shampoo things, you don't need just to understand how it levels at this level, at this level, at this level, and this level, but how do these different structural elements interact with each other and influence each other. Maybe this was also a bias for the self-assembly world, where you, based on the colloid fluid, decide the formulation You mix up the stuff, and then hierarchically they build up. And then you expect your nice, like a Lego game, which self-assembled in your final structure. And with the foam, the things are pretty different. And it's why, for instance, that if you look at your shampoo, it's not just the formulation, but it's also the way you create your foam. So if you're putting your beer and you pull it in your hair, the foam which comes out won't be the same as it is in the glass. Or you see it if you put a beer in a plastic cup instead of a cold glass, you will get a very different foam. So here comes, for instance, the main challenges, at least from my perspective, that the foam properties depend on each and every length scale of this system. And so you want, or we wanted here, to have a simultaneous determination of all these elements in a system which is inherently unstable and multiscale. So it's not something you can measure this with a small angle scattering instrument, taking your foam and doing a tomograph experiment or taking a picture of it, and then at the end combine information. You really need to do it at once. And this is a bit the main story where Julien was involved in combining this real scale, macro scale analysis with the nanoscale imaging. So this is, well, as said, we're going to use mostly image analysis. It's done for surface adjacent bubbles. You see, let's say, probing some square centimeters of your foam. You're combining it with small angle scattering and going more into detail how you what information you can extract. And in principle, you can combine them. I put an example of electrical conductivity. There are many other methods which might be helpful to understand, provide additional information to obtain the structure, the properties of your foam. So for the image analysis, going rather quick, because I think this is for the people in as well known what you can have. You can obtain how much liquid you have by checking, yes, how many black pixels you have on this image. You get a size distribution, which you have at the surface. You can relate it to what you have in the bulk. You can count how long is these black lines, the contours, so getting an idea about the specific surface of this foam. And or you get, for instance, for the plateau border width, if you zoom in into one of these images, you have here one of these borders. If you check along perpendicular to this line, you can get a grayscale profile. So meaning here is it white, with air, it's dark, and it's get white again. And you see if you get it from the full width at the 10th maximum, full width half maximum, how this relate to the bulk one. There's some, at least from my side, some open question on that. But this is some of the information you get from a picture of your foam on the macroscopic scale. And what comes from the microscopic scale, yes, I work a lot with neutron scattering, so we're using this technique to get information from on the nanometer range. So just to how such an experiment schematically show, of course, you need a container to prepare your foam. You need your foaming solution, and then you can prepare your foam by bubbling or by any other methods where you put the foam into the and you have your foam into a container which is transparent to neutrons. You need a neutron beam which you shine through, and then you move your neutron beam up and down, or it's much easier to move up and down the foam column, and you get this kind of data. This is, let's say, typical acquisition time. We are in the scale of the minutes or tens of seconds. So it's something you can easily apply to foams which are moderately stable to get. Also, you can shorten this a bit. So and again, I take the 4 main structural elements showing in the first page. I said this one, forget about it. It's not an information which you can get by neutron scattering or by scattering in general. We have some large objects like the plateau borders, the channels, the vertices. You don't see them directly, but you see the scattering which comes from the interface. It's called the porous scattering. We have some foam films, which gives a signal, let's say, in the intermediate range, and the myosin in a smaller range. Just to those who you have never encountered scattering or small angle scattering, what you have here is the scattering vector, which is inversely proportional to the size of the objects you're probing. So small q, you look at large objects. Large q, you look at small objects. And in the case, it's pretty nice from the foam that you have the different objects which have very different characteristic sizes. Yeah. I just go slightly more in detail on how you get quantitative information on those different structural elements. I said the first one here, this is the big objects in your form, meaning the surface of your plateau borders, of the vertices of all the structural elements whose smallest characteristic size it's very large. You can get these specific surfaces of these big objects. What is also pretty straightforward is the scattering of the surfactant micelles. You basically, in your form, you have a liquid, and in the liquid you have some colloids, might be micelle, but it can be protein, it can be polymers, can be whatever you're using to stabilize your form, and which gives a signal which in principle you can rescale by the liquid fraction, or then you can probe in the function of the shape and interactions between those objects within this liquid. How do we deal with the foam films? Well, the assumption which we made was the foam here is a collection of films which are sufficiently large, sufficiently flat, which are randomly oriented. And out of all these foam films, which are oriented in all directions, there will be some which satisfy a reflection condition, meaning that they're aligned in such way that the incoming beam and the reflected beam have these theta half conditions, like in a reflectivity experiment. And if we do this, we have, let's say, information how much of this foam film we have, and other specific surfaces of these thin liquid films, and the thickness. I mentioned and the contrast condition, and which might be relevant as well. So the question is now, so we have these two experiments, and these were available already long time before we started with this project, is how we do combine them in a single experiment. And we have used, for those who work with foam, they recognize the Taglis foam column, which they kindly made in quartz, which is transparent to neutron. And it's the cell which we are going to use, and we have used for most of the experiments, which is placed into the neutron beam. We take at the same time a picture of the wall adjacent bubbles. This is a bit how the setup looks on the instrument. We can measure the electrical conductivity to have the liquid fraction. We will need this for the quantitative analysis and to take the picture of the forms and doing neutron scattering experiment at once. A bit how does this look in a real experiment where we have generated a foam by gas bubbling, and we follow how this will evolve by simply draining and aging for about an hour. So when we start, we have small bubbles with a lot of liquid. You see the liquid fraction which we get by conductivity is about 10–15%. This is the 2D detector image. It's what we see on our detector, and this is the intensity which we extract by radially averaging this. So if you now let this foam dry or drain, you see here from the bubbles, you start from small, from this bubbling liquid, to all the foam, which is faceted and it's aged. See the liquid fraction goes down, the bubble size goes up. Your signal here evolves significantly, and if we take here our faceted small bubbles, you might guess within this that this signal is not as isotropic as it was before, but we have this plenty of lines which come from the signal from the discrete lamella foam films, which are oriented in all kind of direction. Then if I take what we have from before, you have here information on how this specific surface of your foam evolves with time, with liquid content. We have information on how many films we have, the foam film amount, and the thickness, basically, of these foam films. And you have information of the surfactant micelles, how they evolve their content, and they eventually the shape interaction evolve in the system. So this is the type of information which you get from an experiment. All this is one single measurement, which is evolved, and it's done all at the same time. So if we now take this, it's not to kill you with numbers, but it's a bit to show it's one measurement, it's one evolving form. So we have the size of the bubbles, it's what you get or used to get from the image analysis with its distribution. You see how this evolves with time. It's one form which is aging. The polydispersity index, you have the radius of the plateau borders, and you have what is called the specific image from the foam analysis. At the same time, you have some information, liquid fraction and of the foam film thickness. So here, I think with respect what has been done before, by combining these two methods, or this image analysis and scattering ones, you do get information at once at all the relevant length scale. That's important. The other point is all the analysis, thanks to the combination of methods, can be done in absolute scale. So it's not just we get a qualitative information of the different how thick the foam films are, but also how many they are and how this varies with respect of the other structural elements in your foam. There's one other thing which you can do by combining different techniques, which have the different length scale, meaning one is if we take the plateau border size and the foam film thickness, we call one is gotten by image analysis, the other one by small angle scattering. It's an idea that, well, you can estimate the capillary pressure in the channels, which is in equilibrium balanced by the disjoining pressure. And if you have a disjoining pressure and have a thickness, well, this calls immediately for disjoining pressure isotime, which allows you, let's say, to probe a bit the interaction in a 3D form. I was much more convinced that this is something like a disjoining pressure isotherm 3-4 years ago than I am now. There are many caveats in this, which tells us that, first of all, it's the issues in what is really the plateau border radius in the bulk and what is the capillary pressure. It's a bit what other forces play around and how this we can. But still, I think I'm pretty convinced this is a good measure to estimate the interaction strength in the foam films in a 3D form, which might be very different from what you have in a single foam film. So this, I think, is some of the key output of the work which we have done with Julien. This is the fact that you get all structural elements simultaneously. And I think is in many questions, also applied questions, it's important to know both what's happening at the level of the films and what happens at the level of the bubbles. And I don't see many options to get those information at the same time, other than combining those techniques, and that you have quantitative information on all the length scales. And with this, we would like to show on examples why this has been very useful with the work which have led by Anne Rousseau and Cécile Monteau from Paris. Their scope was to formulate a form to optimize the recovery of metals by oxidizing them. In the broader context was to electronic waste recovery. So you dissolve, you disperse your metal particles in the foam, and you want to oxidize them. And a foam is useful for that because you can use your oxidizer as oxygen in the gas phase. You have a large contact area, and you have a little liquid, which from then you have to purify your metal out of that. And in order to have this system working efficiently, they have to control liquid content bubble size, which relates a bit the amount of reactant which you have available for this reaction, and the foam film thickness, which provides a bit what is the permeability of the gas between the different bubbles. And here you see this is a typical example where you see, yes, you need to characterize the macroscale and the nanoscale of the foam to optimize your process. And for that, they had used a forced Reynolds experiment. So here we have our dry foam here, and we are bubbling the foam in liquid from the top. And you see you're rehydrating the foam. There's a way of controlling what is the liquid content and the bubble size in a rather independent way from each other. So this experiment, here you see it from the liquid way, and here the liquid is coming, and it's swelling the plateau borders. The question is what happens at the level of the films and what happens at the level of the size. So here we do exactly this experiment as it done before. We're doing in our SANS machine, and where from image analysis we get information the liquid fraction. Here's your foam which is drying, the experiment which I showed in the first part. Here you're rehydrating, and then it's drying again. The different colors here, it's different flow rates, but that's what you see here, that the film basically swells at the level of the plateau borders. the bubble size distribution doesn't change significantly. And we see that the film-specific surface does not change, while it does change to one of the plateau borders which swells. So it can decouple the two elements. So this fact is, so we could, by default, from very practical point of view, obtain information of different structural elements which help to better formulate the procedure for optimal metal recovery. The other point which turned out to be super interesting is that we can, by decoupling what we measure experimentally, say for the specific surface, how the one which gets calculated by model system, like in this case with the Kelvin cell, what you would expect by knowing the bubble size and other macroscopic parameters, how does the microscale happens. And this correlates quite well. And so this is, and here that's the part that is quantitative. It allows you both to test theoretical models. So how does your the theory predict the behavior of this system in this particular case where you were dropping your forming solution from the top? And this is also a way of you can explore a much broader, let's say, parameter range just by simulating this or calculating than by doing the experiment. And you know by some experiments this method is applicable for in this case. There's another point which I think is pretty peculiar to neutron scattering. It's the contrast conditions, and how can this be used to probe the forms. And so, to explain a bit this, we come to the question is, what is the concentration or what is the composition of my liquid within the form? So if we, by now I've just mostly described the form as, let's say, as the liquid structure. We have thin films and the liquid channels and vertices. In reality, what we know, the film, all the surface is covered by surfactant molecules. And as you have a high surface to volume ratio, we know that forms are very rich in surfactants. And that's basically all the fundamental of form separation, form purification methods. You say you have your surfactant, you have maybe your molecule has a certain affinity with those surfactant molecules, and you're creating a system with a lot of interface, and then you have enriched whatever you wanted to recover. In addition to that, you do have micelles. If you're talking to surfactant, some other colloids which are dissolved into the liquid. They might or might not be excluded from the film depending on the film thickness. And these are as well very important, as for many phenomena you have, instead for the surfactants, you need an exchange between the molecules at the interface within the bulk, which might be intervene or not. If you're talking about separation, you might have your compounds which are solubilized in these micelles as well. And if you have an exclusion of the micelles from both, and here you have also this anosmotic pressure, which might play a relevant role in determining the structure of your form. If we look this by neutrons, and we work with hydrogenated surfactants, so surfactants which have a normal CH alkyl chain, the contrast condition is very close to the one of air. So in reality, our system looks more like something like that. So I guess every one of you can see those micelles, but you need very sharp eyes to still see the micelles which are absorbed. So if we do this experiment, we really can distinguish between the molecules which are here in the liquid and the one which are absorbed. Which ideally, if you do a chemical analysis of many surfactants you have in the form, it's way more difficult to disentangle this molecule from that molecule here. So this is the question is, how does this vary in the pneumatic form? And just to that video pneumatic form, this is very much accelerated. Here's the time. So here you already arrived by an hour. You're bubbling slowly a foam, which in principle obtains steady conditions, in which you have a foam which is rather humid at the bottom and it's dry on the top. And instead of following it with as a function of time as it was before, we can follow it as a function of the height of the foam. And if everything stays, let's say in the steady state, this doesn't seem to vary much. Again, here, this is by following this for several hours in this type of experiment. And I should remember here, we're looking here what's happening to the liquid channels, the films, and the micelles in the foam. We see how these elements vary as a function of time in a form which macroscopically looks pretty much constant. You can see a couple of things here, a slight decrease in intensity at this level, but then it stops as soon as this gets yellowish. You have a slight decrease, also you have a stronger decrease at the beginning. Here it stops, it stays rather constant. You have a shift of this minimum, think about what is in foam film, but then it stays levels up. And you have a continuously increase of intensity at this level. You see it continuously goes up. So you have a small decrease in specific surface, as in small q large objects, and you have a strong increase in micelle concentration. This experiment was followed as a height of 9 centimeters from the liquid interface. And this increase, which you see, it's the bubble radius goes slightly up, but then it levels off. The liquid fraction, meaning which is proportional a bit to the interface, goes slightly down, but it levels off. And again, you get these specific areas. What was mostly interesting here was in the amount of micelles which the signal continuously goes up. And we can monitor this at the different levels of the foam. And you have here an increase in concentration. It's called this micelle excess, which is defined as the concentration of micelles in my foam divided by the initial concentration of micelles in the foaming liquid, which was 1.5 millimolar of this C14 tab, so a cationic surfactant. And you see this excess here at the highest level, which I've monitored. It's 120 times, meaning you have a concentration of 200 millimolar of surfactant at that level of the foam. So it's by far not dilute system, and it's not an excess of a few percent, but I think it's enormous. So please don't call me rude. You say, okay, this is a straight line which goes through the origin, which fits quite super well. Depends on the perspective for this kind of detail. And you can estimate a rate of enrichment as a function of the height. And again, this looks somehow linear. So then the question arises, where does this come from? How is it possible? In my naive assumption, I said that the liquid of my foam has the same composition as the foaming liquid, more or less. Maybe you can have some deviations. There had been some calculations 20 years ago, and they don't here there in some cases that it wasn't shown that you should enrich it to this, at least to this extent. So if I take here my experiment and continuously bubbling, so I have here a bubble which is born. It's covered by my surfactant. It goes into the foam. It's small and young, and slowly rises. It dries. The bubble itself, it grows in size until here somewhere it dies. And this is the only mechanism I can imagine for which some surfactant can be brought from my foaming solution into the foam. At the same time, you might have the liquid which flows down, which gets mixed by the movement of the bubbles, or the micelle itself can diffuse against the concentration gradient for which the bubbles or the surfactants can go down. So if you see this here, this is my bubble which is going up and aging. The average bubble size goes up, and my specific surface at the same time goes down, vanishing somewhere at this level. So if my specific surface goes down, the surface available to my surfactant goes down as the surfactant goes up, and the surfactant needs to be released when this bubble goes from here to here, needs to be released into the solution. So here you can estimate a net flux of surfactant by simply this decrease of specific areas times the rising velocity times the surfactant axis. Our liquid fraction, well, it goes down, but we see it's rather constant with time. And so again, I don't want to be too rude, said the surfactant, once it's released, it doesn't move anymore from the place where it is. And if we put this, the number of specific surface, which we have from here, from image analysis, and we draw what is we expect as surfactant access, assuming that no surfactant flows down, this is what we obtain here. And so this is probably a pretty rude assumption, but it describes at least the fundamentals of this phenomena, which we have observed also in our previous studies, also in other systems, maybe not to this extent, but it really looks like when you form ages, the molecules which are released, they basically stay at the level where they have been released. Yes.
Can you measure then the superextension of the liquid of the bottom to the
we have measured the electrical conductivity at the bottom. So the surfactant indeed, the surfactant which is present in our foam is not anymore in the solution. And what we observe here, what we have, this is the electrical conductivity, which we calculate by saying how much surfactant is now in the foam with time, which is not in the solution anymore. It describes pretty well the kink here, where you go below the CMC in the foaming solution, and describes, so you have a describes here. But and we have seen also with some UVVs experiments for non-ionic surfactant that the surfactant is really missing in a quantitative way in the foaming solution, which is now present in the foam itself. So here I think it was a bit surprised, and it was our first goal to measure how much surfactant is. But yes, you can distinguish what is the composition of your liquid from the one which is at the interface. I think that's also one of the peculiarities of small angle scattering. And this information here, it can be done only because you have a quantitative measure of all the different parameters and you combine them in once. And I think here there's lots of things which can be done by combining different techniques. Just as a consequence, we estimated that the osmotic pressure at this level is about some 10,000 Pascal, while the capillary pressure is just it's 2 orders of magnitude less. This makes a big difference. And also at this level, the amount of surfactant, the bulk, is much, much higher than the surfactant which is absorbed at the interface, which is also pretty relevant when it comes to purification processes, where maybe the purification might drive through bulk enrichment instead of surface enrichment, and this might be considered in every particular case. And I think also when we discussed just about the cleaning application of surfactants, what is the concentration? It might be just that in your liquid, which you're using for cleaning, you have a much higher surfactant concentration. This might be also a reason why it's more efficient than a simple liquid. And then, yeah, and there might be 10,000 other fields where this might be relevant, which is more to you to see. I've talked a lot about neutron scattering. I think neutron scattering is very, very important in this field, but you have also X-rays, which again, you can combine in a single experiment. It comes to the same problems of before. You need to make sense of the different images to do it once. This is done at the instrument at D22, where you have a X-ray machine and a neutron scattering machine. This is useful for foams, but for many other things. So maybe this get an idea, and you get the 2 scattering signals, which look similar but not identical. And this comes. One thing is you want to use neutrons and X-rays. The primary reason you think of is the scattering contrast. You see the system in a very different way. For the foam, the scattering contrast is not so relevant. Let's say it's a biphasic system. You have a liquid and you have a gas. And in principle, if you look at them with an X-ray beam or neutrons beam, the absolute scale is different, but the information content should be exactly the same. And this is one of the cases where the beam size matters. And if I think here, take here my typical foam, which I've studied till now, you have a few millimeters in size, and your neutron beam, well, it's big. It's 50 millimeters, and what you get, it's a spatially averaged information at the nanoscale. If on the same image I draw my X-ray beam, it is, and it's a relatively big X-ray beam of 1/2 millimeters, it's much smaller. And you see the scattering pattern is completely different, despite you're looking at the same thing. We're illuminating not exactly the same volume, the same portion of the foam at the same time, but here you get information on individual structural elements. So it's not an average. And again, here I think it's important to combine those. What is the effect of one single foam film into a three-dimensional foam, and to have a three-dimensional information or spatially averaged information. And this, yes, this gives, despite being the same contrast, you have distant spatial resolution. There's another thing which I think, which you might explore here. It's when you perform your experiment which what we call air-matched water. So it's a water mixture of light water, H2O and D2O. It's water which has a scattering contrast which is identical of air. So you don't have contrast between the air and your liquid. You don't see the liquid in neutron scattering. For X-ray scattering, nothing changes. Water is water. And so you can do the experiment and probe your liquid structure, basically in the same way I've shown before. And if I do my neutrons, and here I've drawn my foam which is stabilized by a polymer, you don't see the liquid, and you just see the polymer. And this comes because in most of the cases, the fundamental question which we follow is, how do my surfactant, my formulation, my particles affect the structure of the foam? But you can ask also the other way around, how do the fact that you're confining your particles affect the structure of the particles? And this comes particularly relevant, for instance, for particles which are deformable, which are soft. And you expect them to have a very different shape, whether they are in a thin films or not. There are other points that's here, this air-matched water, but you can have examples where you expect your foam to have very different scattering profiles. This is small cells, so you can think about working with very expensive systems or with some foams which you then have to throw away yourself. And I don't want to throw away the quartz column with my electrodes and my prism. So this is something which can think. A bit to run to the last part, I think here, with small angle scattering, I've shown we can measure foam film thicknesses in foams, being X-rays, being neutrons. And if you can measure the thickness, we can in principle measure how this thickness fluctuates. And this is done with neutron spin echo, which, let's say, I apologize to the people working with NSA. It's a bit the equivalent of dynamic light scattering with respect to static light scattering for in the light scattering domain. But so we measure the fluctuations of my structure in the nanometer scale and some nanosecond in the nanoseconds. So here the same column, which is now installed on the neutron spin echo TILL, and you get some noisy data, because here, while with small angle scattering, we can measure in the sub-minute scale. Here we have to measure, let's say, ideally few hours. This has been reduced to the strict minimum of half an hour. But still you get some noisy points, which to my opinion, spin echo always delivers noisy points. But you should don't tell to the colleagues. Still you extract from here a decay rate, which scales with Q squared, from what we've seen. And if we imagine this relaxation mode for the thickness, assuming we are seeing thickness fluctuations, this relaxation mode should scale with Q squared. If this is the fluctuation of the independent fluctuation of interacting films, whereby this scales with the cube of the thickness and the second derivative of the disjoining pressure isotherm, which has been determined the way we've shown before. And if you put the numbers in just from this independent experiment, this is what we can predict. So I want to be very careful on this point. This is is this the question? Are we seeing a peristaltic mode in a foam film, or are we seeing something completely different? As we have some planar films or interfaces, there are many things we scale with Q squared, and it's just a coincidence that this fits that well. And if it is the case, is this information helpful to understand how coalescence mechanism will go? So this is something, I don't know if we can go to so far relying to my first slide, but I think this is something which will be interesting to look into more carefully. Now I stop with forms. I think it's a bit an overview of different techniques, and I want to break it down a little bit into its structural elements. And starting with the thin liquid film, this is the way in small angle scattering we have probed them. So you have spatial average of random orientedly films. This comes with a cost that you have a limited resolution in the scattering profile along this normal axis, as you have the signal which comes from very few of those films, which is superimposed to all the others which are scattered in any direction. And these films are not perfectly flat; they are all curved, and this generates an effect which we have not yet taken into account. If you take a single film and you orient it properly, well, you can do basically the same experiment, except with the fact that you can do it in a neutron reflectometer, which has a much higher resolution. And even though these films are curved, it's something which can be deal very well with that. So this is a different type of experiment which can give you a much higher resolution on what is the composition or what is the film structure, the structure within a thin liquid film. Just to schematize this is the small angle scattering. It's a big beam going through a lot of bubbles, and you will hit some of the ones in the right orientation, which go in all directions. You take the average, the radial average of that. Well, if you work with a single film, you hit one film and you have your interference pattern in this direction, which you're probing. And this is how was our bamboo foam looks like. And I was very jealous to the pictures of the bamboo foam made here, which looks very much nicer than all those ones. But still, it's a foam film which does the job. You can illuminate in the reflectometer for a few seconds to get the signal, and you can get an SLD profile across the foam film thickness, which you get. We might want to study the film composition along your z-axis, basically, along your film here. Last slide. I'm always, but I think it's important to study the air-liquid interface in the context of studying foam, but I'm still not sure how much it is useful to understand the foam. So is it good? Is it not? Should we invest time in understanding them? It probably depends on your system. In general, the typical thing where we also simulate a bit how is the drying of the foam. It's you have your surfactant molecules at the interface with some movable barriers. You compress them, you change basically the composition. By this, you change the surface energy, and you look at the structure, how this evolves by this kind of movement. This is experiments which are done, Thierry, since ever since, or since 20, 30 years, something like that, the Langmuir isotherms with this. But this is, and it's very useful for all the people studying the air-water interface or what is happening at the monolayer. When it comes to the to forms, I think it's also important to combine the structural information of the film with something which is the mechanical properties at this interface, because this is an information which can help understanding the elasticity maybe of your films. Again, here you're working with a single air-water interface, and it's not a thin film. And so you should, in principle, do this in the lab. 2 different experiments. In one you explore the structure, in one you explore the rheological properties, and then you combine the information. Unless you can do otherwise, you can combine them in a single experiment. There's something which is more, let's say, newer, and we are seeing it being as very relevant, is the fact to replace the Langmuir trough, where you're basically doing a directional compression with some, which is the quadrotrough developed by Young. Where you have basically an elastic rubber and you have your molecule here. And you can, basically, if you want to compress, you do the compression by moving these arms. So you're doing an isotropic compression. And even for small molecules, my colleagues on the refractometer are seeing significant differences in the behavior if you're compressing like this in one direction, or if you're homogeneously compressing from one direction. And what you can do also is, well, you can move basically all of the four arms independently, so you can shear your system and looking at the structure of the sheared interface and how this evolves. So I think is how much this information which helps understanding the forms. Well, we will see. Maybe yes, maybe not. But I think this kind of experiments will definitely help understand better the behavior of some molecules at the water interface. So I come to the end of the slide. So I think it's not just because I'm working at the Neutron Scattering Institute, but I think neutron scattering has this important role to play in the domain of form and form characterization of three-dimensional forms, and to extract the nanoscale structure of these systems. Even though it's very important, without complementary information, without combining them with the other experiment, it's only partially useful. And I think there's some more advanced experiments, let's say non in broad user operation, not deployed for everyone, where you can extract lots of valuable information, and this has to be seen. If some of the things ring a bell, as I'm here this afternoon, as I get also paid to do advertisement, we have a proposal deadline, and please come and speak to me. But here again, a big thanks to Julien, who has done a lot of this, all this initial development. He has done incredible work. Olivier Diard, who has introduced me to the world of form. Here, the instrument responsible for the neutron spin echo and the Sachs machine. Wipke and Reinhard Miller for some useful comments for interpreting the Meissel enrichment, and all the other people at EL to set up those things. And here we have some of the reference of the work which I've shown you. And thank you very much for listening.